So in this video here, I'm going to show you how to do Lewis dot structures for covalent molecules. Now previously we've done that for ionic ones, just like we got up here. The difference though is that in ionic ones you want to form a ring of 8, and one atom is going to steal electrons from another in order to get that ring of 8. So there's going to be a winner and a loser. Let's go ahead and see how it works. So first of all, we put the valence electrons in. If you have forgotten how to do that, you look at your periodic table. At the top of the column is a Roman number, which tells you how many valence electrons it has. So chlorine has 7. 1, 2, 3, 4, 5, 6, and 7. And sodium only has 1. So we put 1 in over there. And you can see we've now created a ring of 8 around chlorine, but not a ring of 8 around sodium. So chlorine is the winner. Sodium, that's the loser there, right? So chlorine stole the electron away from sodium. Since we have a winner and a loser, this is what we call an ionic bond. That's where we left off. However, with covalent bonds, it's going to be different. So in covalent bonds, you're not going to have a winner and a loser. You're going to have 2 winners. Everybody's going to have a ring around them that they want. Let's go ahead and look at how this works. So the first thing is every atom, yay, gets to win. Not like sodium chloride. Every atom wants to have a ring of 8. The only exception, of course, we talked about hydrogen. Hydrogen only wants to have a ring of 2. Okay? Everybody else wants to have a ring of 8. Now, how are we going to get this so that everybody wins? The only way everyone can win is we have to share the electrons there. And what we mean by sharing is we may have to count them more than once. Okay, here's how we're going to do it. So first of all, we're going to count the number of electrons we need to have if everybody got the ring that they wanted to have in a perfect world. So we have, this is how many electrons we want to have. And then the next thing we're going to do, step number 2, we're going to count how many valence electrons we do have. And what we're going to find out is we don't have enough electrons. So we subtract the 2, and the difference will tell us how many electrons need to be shared. Now I gave everybody a worksheet, so let's go ahead and turn to that last page there. It says activity 9.8, Lewis dot structures here. And we're going to go through the procedure. We'll do a couple of examples together. So this one here is a covalent. It is nitrogen trifluoride. You have 1 nitrogen and you have 3 fluorines. So you have 4 atoms. Pretty heavy-duty math, right? 4 atoms. Everybody wants to have a ring of 8. So if we do 4 times 8, right? 4 times 8, that means we wish we had 32 electrons. If we did, it's perfect. Everyone gets to have a ring of 8. But how many do we actually have available? Nitrogen only has 5, and fluorine has 7. But we have 3 fluorines, right? So these are the number of valence electrons if I look at the top of the column. So this is 26 available electrons. I wish I had 32 to make rings of 8. I only have 26, so I'm short. Let's subtract them. 32 minus 26 is 6. So that means we have to count 6 of them more than once. We got to share them in order to get it to work. Let's go ahead now and build our molecule. So we have 1 nitrogen and fluorines. Remember we said the most likely organization is the nitrogen goes in the middle, yeah? So there's 3 fluorines, yeah? Okay, now I know according to this, let's make a different color so you can easily see it. I know according to this I need to share 6. So 1, 2, 3, 4, 5, 6. That's the ones I'm going to share. And now I'm going to put in the others. So I shared 6, I have 26. So I have 20 more electrons to put in here. Here we go, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Now I've got 26 electrons. Did everybody get a ring of 8? There's a happy guy. There's a happy guy. There's a happy guy. And this guy has a happy ring too. Everybody got a ring of 8, but the only way I was able to make that happen was I had to share. You see the 6 green ones there? I had to share those 6, so we're counting them more than once, right? So like these 2 got counted in 2 rings. So now I can recognize, since everybody won here, because I shared electrons, that must have been a covalent bond. Let's go ahead and try another one. So if you turn your page to the last page there, let's look at number 7 here, right? This is sulfur trioxide, sulfur trioxide. I have 1 sulfur and I have 3 oxygens, so I have 4 atoms. And each one wishes it had a ring of 8. Once again, we wish we had 32. 4 times 8 is 32. How many do I actually have? Sulfur has 6, and the oxygen has 6. I have 3 oxygens, so that's 18. So my total is, I have 24 available valence electrons. That's not enough. I wish I had 32. 32 minus 24 is 8. So I don't have enough. Okay, so how am I going to do that? Sulfur trioxide, we're going to assume the sulfur is probably in the middle, and then I got 3 oxygens around it. I'm going to share 8 electrons, right? So let's go ahead and share them. 1, 2, 3, 4, 5, 6. Uh-oh. What am I going to do with the other 2? Well, I'm not going to put them up here, right? If I put them up here, that's not sharing them with the other guys, right? So that's no good. Let's go back here. I want to share them. Maybe I have to put them here, right? So I'm sharing 8, but this guy I'm actually sharing 4, 2 and 2. Can I do that? Sure you can. We're going to talk about what this is in a second, right? Now let's put in all the other electrons, right? So I shared 8. I had 24, so that means I have 16 to go. 1, 2, 3, 4, 5, 6. Ring of 8. 7, 8, 9, 10, 11, 12. Ring of 8. 12. 13, 14, 15, 16. Now I put in all my electrons, and look. That's a ring of 8. And sulfur has also got a ring of 8. Little bit of a trick. So I could put 4 in here instead of 2. And this is what we call here a double bond. 2 electrons are a single bond. 4 electrons would be a double bond. Aha! So we could put in more than 2. Now you can't put an odd number in there, right? Every 2 is a bond. So 2 electrons would be a single bond. 4 electrons, like you just saw, is actually a double bond. 6 electrons would be a triple bond. Oh my gosh. Could we put in 8 electrons to make a quadruple bond? No, you can't do that. And the reason is that if you did that, nobody would have the correct number of electrons. So you can't go that high. So you can go as high as triple bonds. That has the most electrons. So it must be the strongest type of bond, but it's also the shortest. So the stronger the bond is between the 2 atoms, the tighter it pulls them in together, right? And it makes them short. Okay, let's see if you guys understand. We're going to do one now that's off your chart. You don't have this one in your handout. Let's go ahead and try carbon dioxide, CO2. Let's see if you can do it. So let's go through the steps, right? So here we go. We have one carbon and two oxygens, so we have three atoms. Now, hydrogen's not in there, yeah? So everybody wants a ring of 8. 3 atoms times 8 would be, we wish we had 24 electrons. But how many electrons do you actually have? Carbon has 4, and each oxygen has 6. You have 2 oxygens, right? So 4 plus 6 is 16. 24 minus that means I'm short 8 electrons. So we got to share them. That's how I know this is going to be a covalent. We got to share them. Okay, here we go. Remember how we do it, guys? You have 1 carbon and 2 oxygens, so we're going to assume carbon goes in the middle. All right. Now we put in those shared electrons, right? We have 8 of them. 1, 2, 3, 4. Now we don't want to put them up here, right? Because that's not good. Now we're not sharing them. So that's no good. So where are we going to put those guys, right? 5, 6, 7, 8. Okay? And now we've got our 8 shared, but we had 16 total, so we got 8 more to go. Let's put in those other 8. 1, 2, 3, 4, 5, 6, 7, 8. Did I make my ring of 8? There's a ring of 8. There's a ring of 8. There's a ring of 8. Winner, winner, winner. Very, very good. Now we could go ahead if we wanted to, and we could do like the fancy chemists do, and we could go ahead and make this into a line diagram. So there's that, there's that. We have 4, that's a double bond. 1, 2. We have 4, that's a double bond. So there's the molecule of CO2. Now wait a second though. Is there always just one way to do it, or is there another way we could have done this? Let's take a look at this one more time. Let me draw these back in. I think there may have been another way we could have done it. Okay? Let's do it again. I have 8 shared. 1, 2, 3, 4, 5, 6. Oh, wait a second. Couldn't I do it like that? Is that possible? Let's see if that works. I got 8 shared. I have 8 more electrons now to put in there, right? Let's see. 1, 2, 3, 4, 5, 6. Where can I put the other 2? How about over here? Did that accomplish the same thing? Let's see. Ring of 8, ring of 8, ring of 8. Oh, there was a second way I could have done it. And let's go ahead and draw the figure for this. There's your CO2. Single bond, and now 1, 2, 3, triple bond. That's a really complicated one, so I didn't put this on your handout there. Go ahead and see if you can do the last page, both sides. See if you can do the covalent structures.